Compare these two architectures. On the left, user input follows a straight line to retrieve a specific database row. On the right, that input enters an AI model, branching into a cloud of potential outputs. Applying standard management to this variable system creates immediate friction. Traditional software runs on deterministic systems. Every line of code is a fixed instruction, meaning a specific command guarantees the exact same behavior every single time. AI operates as a probabilistic system. You can provide the exact same prompt twice, but the output may change based on the model's internal weights, the context of the conversation, or even the specific version of the model being used. This means an AI product manager is no longer managing static features. Your core responsibility is now the oversight of variable, intelligent behavior. In a controlled prototype environment, these systems look remarkably stable. When prompts are curated and data is clean, it appears highly reliable. That stability often vanishes in production. Once real users introduce unformatted text, contradictory logic, or ambiguous requests, the model is forced to navigate scenarios it was never specifically tuned to handle. Moving from a successful prototype to a functional product requires a change in how we think about quality. Standard software testing assumes you can map every possible path. With AI, the number of paths is effectively infinite. This shift requires a new operational framework, built on continuous evaluation pipelines, driven by multi-layered metrics, and system-level architectures that don't just rely on the model being smart. Without a framework designed for this volatility, the impressive results seen in a demo are difficult to replicate at scale. To understand how to build that stability, we have to look at how we measure these systems. Standard software relies on unit tests, binary checks that confirm if a function returns a true or false value. But you can't write a binary test to determine if a model's summary of a 20-page contract is actually good. Instead, product teams use evals, structured, automated tests that measure performance against specific criteria over hundreds or thousands of examples. The core of this process is the golden dataset. This matrix organizes a wide range of year inputs against specific grading criteria, like accuracy, tone, and refusal behavior. A golden dataset must include your known failure modes. By running the model against these difficult edge cases, you can see exactly where the logic breaks before a user finds it. These evaluations are a continuous requirement. They are the only way to prove that the system is actually improving over time. Whenever you update a prompt or change the underlying model, the golden dataset acts as a benchmark. It ensures that fixing one problem hasn't caused 5 new regressions in other areas. Without this dataset, deployment decisions are based on anecdotes and small samples. With it, every change is backed by empirical evidence. Even with perfect testing, models hallucinate. As a product manager, you cannot promise to stop the model from making things up at the mathematical level. Your role is to build a system architecture that catches those errors. This flowchart shows 3 specific gates designed to filter and verify information. The first gate is grounding. By using retrieval augmented generation, you force the model to look only at a trusted database. The second gate adds explicit citations for every claim. The third gate uses confidence thresholds. The system calculates how certain the model is. If that score falls in Torvalds zone, the output is blocked entirely. This architecture shifts the focus. You aren't just trying to build a smarter model, you are building a controlled environment that prioritizes user safety and trust. These architectural gates define the product's design. If the confidence threshold isn't met, the interface needs to communicate that limitation clearly. The most important feature of an AI interface is the ability to say, "I don't know." Forcing a probabilistic system to guess is what leads to the most visible product failures. This creates a natural path for human escalation. When the model hits a low confidence state, it should automatically hand the query over to a human who can provide a deterministic answer. This escalation is vital for high-risk scenarios. In medical, legal, or financial applications, the system shouldn't act autonomously. It flags complex cases for human review. A successful AI product doesn't strive for total autonomy. It coordinates the speed of automation with the reliability of human judgment. Standard SaaS metrics like retention or daily active users only tell half the story. To understand an AI product, you need to track how the model itself is behaving in the wild. This is the 4-layer metric stack. It provides a comprehensive view of how a non-deterministic product is performing. The user and business layers track your outcomes, things like task completion, revenue impact, and the actual cost savings generated by the automation. The AI quality layer tracks the model's behavior. Here, you measure specific traits like groundedness, hallucination rates, and correct refusal of inappropriate requests. The operational layer tracks the infrastructure. This includes system latency, the frequency of human handoffs, and the variable cost of every user interaction. Consider an AI support agent. It's not enough to know how many tickets it closed. You have to balance that against the cost per conversation and the accuracy of those resolutions. Monitoring all 4 layers ensures the product stays viable. It prevents a situation where the model is highly accurate, but so expensive it loses money. Once you have the architecture and metrics, you have to decide where the model comes from. You can build your own, fine-tune an existing one, or simply use an API. For general tasks like summarizing text or drafting basic emails, off-the-shelf APIs are usually the best choice. They allow the team to focus on the product rather than managing the infrastructure. Fine-tuning becomes the right choice when the system needs a highly specific tone or domain knowledge that isn't found in general models, or when you need to optimize for lower costs at a very high volume. This matrix shows the trade-off. Self-hosting or building a model from scratch is only necessary when you require total control over privacy, custom architecture, or extreme scale. By letting business requirements drive the sourcing decision, you avoid the trap of over-engineering a solution when a simple API would have solved the user's problem. Launching these systems requires a staged pipeline, moving the AI from prototype through baseline evaluations and internal testing. Here, teams use red teaming, deliberately trying to break the model's logic to reveal hidden weaknesses. The small cohort beta exposes the system to real-world variability, identifying how users actually phrase requests. In full production, the focus shifts to hardening, detailed logging, and strict fallback behaviors, with continuous feedback loops ensuring consistency. Because AI is probabilistic, roadmaps must include room for discovery. You have to assume the model will behave in ways you didn't predict, requiring time for iteration and tuning. Following this rigorous pipeline is the only way to turn an unpredictable model into a stable, reliable enterprise product. The ultimate goal is not to ship the most impressive technical demo. It is to build a system that users can rely on every single day. Traditional product management often focuses on whether a feature is possible. With AI, the question is no longer, can we build this? The questions that matter now are, should we build this? How do we measure quality and control it at scale? Mastering AI product management is more than understanding the tech. It is the discipline of engineering trust within systems that are inherently unpredictable.